Hi, let us continue with our discussions about the design of peg footing subjected to the axial loads together with the moment acting in both the major and the minor axis. So far, we have decided the amount of reinforcement bar to be embedded in the peg footing, making sure the AS provided is greater than the AS required, and the AS provided fall within the range between the AS min and the AS max. The following step, it will be checking the shear resistance. There are 3 shear resistance that we need to deal with. Let us first deal with the shear resistance located at the shear plane, placed at 1D from the column face. Since we have moment acting both in the major and the minor axis, that means we need to check the shear resistance at the shear plane both in the major axis and the minor axis. To do so, we will need to first determine the locations of the shear plane. You know that it is located at the distance of 1D effective depth from the column face. As for this shear plane, it is also 1D from the column face. We have calculated the D previously. In the major axis, the effective depth is 519. In the minor axis, the effective depth is 507. We also know the size of the column. The major axis is 300 and the minor axis is 150. Now we need to determine the distance Z1 and Y1. This is calculated by taking the width of the peg footing, which is 2.4 meter, minus the column width, which is 300, divided by 2. You get your Z1 equals to 1050. We will do the same to determine the Y1. Take the width of the peg footing, which is 2.4 meter, minus the width of the column, 150 mm, divided by 2. Your Y1 is equals to 1125. Next, we find the locations here, which is located at 1D distance from the column face, resulting the balance width here xz equals to 531. Take 1050 minus 519, it gives you 531. You will do the same to determine this distance. Take the Y1, which is 1125, minus the effective depth 507. That gives you the xy equals to 618. You need to determine the shear force. The shear force is determined based on the stress outside of the shear plane. In the major axis, we are referring to this area, whereas in the minor axis, we are referring to this area. Having the locations of the shear plane identified, then you can determine the shear stress here. This can be done by doing the interpolations between the shear stress. The calculated ultimate shear stress, based on the formula here, we have done it previously. Take those shear stress, identify the distance from the minimum shear stress. We do interpolations for you to find the PS, both for the major and the minor axis. The PS varied slightly due to the differences in terms of the dy and dz, as well as the z1 and y1. Once you have obtained the PS, now you need to determine the plane shear force. Take the area of the stress at this region. This is calculated by using the equations of the trapezoid. Take 1/2 multiply PS plus P maximum multiply the X here. That means take 1/2 multiply this plus this and then multiply this. You will do the same for the minor axis. Then you get your shear force. This shear force appears in per unit width. For the major axis, you need to multiply this width, which is 2.4 meter. Take this, multiply the 2.4 meter, you get the shear force equals to 310.6 kilonewton. As for the minor axis, we are talking about this shear plane. Take this shear force, multiply this width, and the width is equals to 2.4 meter also. You get your total shear force equals to 358.1 kilonewton. Later, we will need to check the shear resistance against the calculated shear force. The shear resistance is determined by these two equations. The larger value, it will be the shear resistance at the shear plane of 1D from the column face. The two equations will require the factor K as well as the rho 1. Therefore, we will need to calculate the K and the rho 1 first. The K is in the functions of the effective depth. The effective depth for the major and the minor axis are given here. Plug in the number, you get the K equals to 1.62 and 1.63. The K is less than 2.0. You will use this 1.62 and 1.63. And then you find the percentage of reinforcement bars. The AS provided in the major and the minor axis are the same, which are equals to 1923 divided by BD. Since the pad footing is a square section, the B will also be the same, 2.4 meter. As for the effective depth, D, they vary slightly, which are equals to 519 and 507 for the major and the minor axis. You get your rho 1. The calculated rho 1 here is less than 0.02. You will use the calculated rho 1. Next, you will substitute the values into the equation. For the major axis, you use the K and the rho 1. As for the minor axis, you use the K and the rho 1. SCK equals to 30, as given in the question. The B for both major and minor axis are the same, which is 2.4 meter, and then you use the right effective depth for the major and the minor axis. This gives you the VRDC equals to nearly 400 kilonewton. The VRDC represents the shear resistance of the pad footing, taking into considerations of the reinforcement provided. And then we calculate the VRDC minimum. Substitute the K into the equations. FCK equals to 30. The B 2.4 meter, and then the effective depth. You get your VRDC minimum equals to nearly 490 kilonewton. Compare the two values. The bigger value will be the resistance of the pad footing. Same goes to the minor axis. And then check your VRDC against the VED, which is the load. make sure your resistance is greater than the load. In this case, the resistance is greater than the VED. Therefore, the shear resistance is acceptable. If you observe the calculations, remember previously we mentioned the minor axis, it will be more critical when we provide a square sections for the peg footing. This is mainly due to the smaller effective depth in the minor axis. Also, the minor axis have a smaller column width, resulting a greater Y1 distance as compared to the Z1. When this distance is longer, more stress will be engaged in generating the moment at the column face. As a result, you will get a larger moment. When you have a larger moment and your effective depth is smaller, that means you're going to require more reinforcement bar to take the moment as compared to the major axis. In fact, if you wish to make the arrangements of reinforcement bar more optimized, you can swap the arrangements of the reinforcement bar, taking the minor axis to be the main reinforcement, whereas the major axis with the secondary reinforcement. This you can take advantage of a larger effective depth. When these two effective depths swap, the amount of reinforcement required in the major axis will increase slightly, and the amount of reinforcement in the minor axis will reduce slightly. This might lead to slight saving in terms of the amount of reinforcement bar, provided that they fulfill the minimum AS. In terms of the shear resistance, also because of the Z1 and the Y1 distance, minor axis will engage more stresses outside of the column. Indicates that when you have a shorter effective depth, a larger regions of stress outside of the shear plane shall be engaged. As a result, you will have higher total shear force in the minor axis. And then in terms of the calculations of the shear resistance, it is also based on the effective depth. If you wish to make the arrangement of the reinforcement bar to the greatest advantage, you may swap the arrangements of the reinforcement bar so that the minor axis become the main reinforcement and the major axis become the secondary reinforcement. As a result, this will have increased slightly the resistance in the minor axis, but slightly reduce the resistance from the major axis. Those are the influence of the arrangements of the reinforcement. You can follow this arrangement. As you can see for the result, not really significant differences. You can also choose to make it more optimized by swapping the arrangements of the reinforcement. Just that, once the reinforcement is being swapped, you have to make sure the effective depth used at the following calculation step be consistent. If you find difficulty to imagine the implications, you may sketch the diagram, look at the cross sections of the shear plane, and then you can imagine the influence. This explains the reason why the minor axis, when we talk about the square peg footing, is more critical. In the following videos, we're going to check for the punching shears, as this is another important aspect in the design of the peg footing. Stay tuned.